Right. So thank you, first of all, for the kind invitation. Very excited to be giving this seminar today. And as Guam mentioned, I'm gonna talk about, I'm gonna give you an overview on the Open Run, and I will be focusing on artificial intelligence and machine learning challenges for the Open Run and some experimental frameworks for research in this ecosystem. Right. So the outline of today's talk will be some introduction on the Open Run, and specifically talking about some interfaces that enable interoperability between the various components of the cellular networks. Then I will go through some workflows for artificial intelligence and machine learning applications in the Open Run, also mentioning some use cases of interest. And then I'm going to talk about Open Run Gym, which is a framework that we developed at Northeastern. And this framework allows you to carry out experimental research in the Open Run ecosystem through open source software that anybody can use and experiment upon. And finally, I will conclude the talk with some security challenges and novel opportunities that this ecosystem enables. So without further ado, let's begin with our vision for the Open Run. And this is very much shaped by the ORAN vision. So ORAN is this framework that is taking a lot of attention on the Open Run ecosystem. And basically, this framework endows the cellular network with an approach that is flexible by design and allows the network planner and the network manager, so for instance, network operators, to perform dynamic control loops with the open interfaces that ORAN standardizes and that I will introduce later on, and some open APIs. So the general idea is that you have your network elements, so you have the base stations that are not monolithic anymore. So once upon they were like formed by a single entity that was carrying out all the tasks typical of a cellular base station, but now we have what is called network disaggregation. So the base station is split into various elements, such as the ones in the yellow boxes that you see on the picture. So we have a radio unit, also called RU, a distributed unit that is called also DU. And then we have various planes for the central unit, which is the CU. And all of these together carry out the functions that are typical of a cellular base station. And what ORAN does is standardizing the interfaces from these elements to what ORAN introduces as network controllers or run intelligent controllers, also shortened as RICs. And here we see the two that are standardized by ORAN, where we have a near real-time controller, which carries out loops, control loops that we will see later on at tighter time intervals. So more time-sensitive control loops. And then we have what is called a non-real-time run intelligent controller, or RIC, that allows the telecom operator to carry out control loops, but that have larger time scale, for instance. And all of these allows the operators to implement some custom control logic based on some network abstractions that are in place. So as I was saying, the traditional approach is based on what is called a traditional and monolithic base station, where we have a single element. But then with ORAN, this is split into various different elements. So we have our DU, distributed unit, that takes care of the higher layers of the physical layer, the MAC layer, and the RLC layers. And then we have some centralized unit, both UP, that is for user plane, that carries out some PDCP and SDAP protocols functionalities. And then we have a control plane for the CU that carries out the RRC messages and the PDCP functionalities that pertain to control. And all of these can be deployed in the cloud. So in what ORAN calls an O-Cloud data center that is deployed at the edge cloud of the network. And these DUs and CUs component connect to what is called the RU, or disaggregated G0B. That is what actually is the cell site. And this element takes only care of the lower layers of the physical layers, the lower functionalities of the physical layer, such as the precoding, the beamforming, and the actual RF transmission of the cellular signal and their reception of these same signals. And all of this is controlled by the controllers that Oran introduces. So I was mentioning the near real-time and non-real-time run intelligent controllers, which take care implementing control loops between each of the network elements at different time scales that we will see later on. And these are deployed in the most common deployment scenario. These are deployed in a regional cloud. So we have what is called the O cloud deployed in a regional data center, for example. So this is pretty much the split architecture that Oran is working with, also enabled by the disaggregated network functionalities introduced by the 3GPP. So basically, from a logical point of view, we have what is called the O cloud. So we have some cloud data centers, and here we deploy a service management and orchestration framework, also called SMO, which takes care of the management of our network and orchestrating very many functionalities of the network. For instance, the deployment of our network services in the various general purpose hard pieces of hardware that are in our network. Because let's remember that also some of these components once require specialized units to run. So for instance, if you had a monolithic base station, you needed a specialized unit for that specific piece of hardware. But now with this disaggregation of the components that I just shown, like the DU and the CU, can be run on generic purpose hardware and without much specialized hardware, while the RU still needs specialized hardware to be able to transmit the actual cellular network signals. So going back to the cloud, we have a service management and orchestration framework that can orchestrate all the services in our network. And inside this is the non-real-time RIC that is designed by Oran. Then we have a near real-time RIC deployed in the cloud, and then we have the various pieces that carry out the functionality of the base station. So, for example, we have the RU, the DUs, and the various layers of the CU. But we also have what is called an O E0B, which carries out the legacy E0B operations in the Oran ecosystem. And all of these is shown, all of these components like the RU, DU, and CU are shown in the drawing as a single element. So we see that we have one RU, one DU, and then we have one CU with control plane functionality and user plane functionality. But of course, you can think of a cellular network in which you have many CUs that control a certain number of DUs, and also a single CU can control multiple DUs. And then we can have also multiple RUs in the network. So all of these, as the network becomes larger and larger, scales with the size of the network. And then in the same way as we can have multiple CUs and multiple DUs or RUs, we can also have multiple near real-time RICs that are interfaced to a common non-real-time RIC. So how are all these components interconnected? So they are interconnected through some interfaces, which are in part defined by Oran. So for example, here we see just a high-level overview of these interfaces, and I will go into the details of what all of these interfaces do. But we see that, for example, the components of the base station are connected to the RIC, the near real-time RIC, through an E2 interface, while the two RICs are connected among each other through an A1 interface, for example. And I will come back to these interfaces shortly. Then we have other interfaces, which are the ones in the dashed line. And these other interfaces help interconnected the various CUs of different, potentially different operators, or the same operator with more CUs and more network elements. So the dashed interfaces interconnect multiple CUs among each others, for example, or each CU with the DUs that it's controlling. And then we have between the DUs and the RUs what is called open frontal interfaces, both from control and management planes that actually allow the DU to talk to the RU, as we will see shortly. Going back to the near real-time rig, we have that one of the main tasks of the near real-time rig and one of the main functionalities that this component offers is to oversee the CUs and DUs in the network, and specifically to gather data from these components, so to gather data from the CUs and RUs, and from the CUs and DUs, and to implement some control loops based on this data that are carried out in what is called XSUB. So the XSUBs are some third-party applications that run in the near real-time rig, and where the operator can program their own custom logic. So you can think of these as plug-and-play blocks that can be hosted in the near real-time run intelligent controller. And each one of these blocks can carry out some very specialized functions and control loop based on the data that arrive from the run, so from the base station. So for example, one XSUB can get the data from the base station and perform some forecasting on how the traffic will be at a later moment. And then based on this, maybe can also trigger some functionality to the base station. So for example, to modify the scheduling policy that's running in the base station, or the allocation of resources to the different users to grant priority users more resources. And all of this is standardized with some functionalities, and can also allow different implementations based on the actual goal of the operator. Then the rig has also other internal components that handle the security aspect of the controller, some subscription management. So for instance, to manage the various base stations that are connected and that are controlled by the rig, and then some conflict mitigation operations. And talking about conflict mitigation, I was mentioning that there can be some XSUBs on the near real-time rig that carry out some of the operations that the telecom operator wants to do. So for instance, they can modify the configuration of the base station. But what happens if multiple XSUBs, so multiple applications, try to modify the same functionality that the base station is exposing? So for this reason, we need some conflict mitigation component to guarantee that all the XSUBs that we have are not taking actions that directly conflict with one another. So for example, we don't want to have multiple XSUBs that control the same resources of the same base stations, because they will take conflicting actions. So for example, this is what is called a direct conflict. So if two XSUBs control the same parameters, so the same, for instance, allocation of resources for a certain base station, but we can also have what is called indirect or implicit conflict, in which we don't exactly control the same parameters, but we control some parameters that have an effect on some other functionality of the base station. As an example, we have one XSUB, so XSUB1, that can control a certain parameter, so the number of physical resource blocks, so the number of resources for a certain slice. And this XSUB can decide to decrease the resources of the slice for if the slice is not serving a lot of users. But then we can have another XSUB that controls another parameter, which will trigger a handover of the cellular users if there's a slice that is being shortened in terms of resources, for instance, by XSUB1. So this XSUB, for example, can go in conflict, and so that's why we need to have some conflict mitigation component inside the controller. After the near real-time, we have the non-real-time rig and the SMO. So the near real-time rig runs inside the SMO, so the service management and orchestration component. And we have that this takes care of and interfaces with some functionalities of the SMOs. And then we have, based on this, we have some functionalities that the non-real-time rig takes care of. So for instance, control loops with time scales that are larger than what exposed by the real-time rig. And then we have a host of shared functionalities between the SMO and the near real-time rig. And the near real-time rig, one thing that could do is to mandate some policies that the near real-time rig needs to carry out, for example. I was telling you that all the components that we have are connected through some interfaces that Orani standardizes. So the first interface that I would like to mention is the E2 interface. And this interface is actually connected in real-time rig to the CUs and DUs of our network, so of our RAN, but also to the legacy InnoDB. So the task of this interface is to manage the reporting of information from the base stations, so from the DU and CU. So basically, the base station CU and DU will report some performance indicator to the near real-time rig to give the rig a sense on how the network is behaving. And then the near real-time rig, based on this information and based on the XApps that are executing inside the near real-time rig, can take some control actions to modify the running configuration of the CUs and DUs. So the flow would be that the XApp subscribes to some of the functionality of the DU and CU, gets the data from these components, and based on the data, maybe it's running some algorithm that decides to take some control on the functionality of the base station. So for example, to resize the resources that each base station is using for a specific group of users. Another interface that we have is what is called the A1 interface. And this interface is between the non-real-time rig and the near real-time rig. And the task of this interface is to handle the policy management and the data transfer between the non-real-time rig and the near real-time rig. And also one of the other tasks is to carry out the management of the machine learning models that are typically stored on the non-real-time rig and to deploy them on the near real-time rig as needed. So this is a more higher time scale kind of control that can happen and operations. Then we have the O1 interface, which connect the non-real-time rig to the remaining components of the network. And this interface is used to carry out some maintenance operations and to deliver some control and management services to our RAN and rig components. So for example, some of these services can be the fault management service or heartbeat management, where heartbeat is a signal that the RAN and rig components transmit to let the non-real-time rig know that they are still running. We can have some performance assurance and reporting of key performance indicator. So for instance, some metric reports from the various components to the non-real-time rig through the O1 interface. And then we can have some configuration and startup of the components that are carried out through this O1 interface. So for example, if you want to deploy one of these components like a CU or IDU, the command to actually deploy these components can travel through the O1 interface from the non-real-time rig. And then we have some other tasks that take care of software management and software dispatchment on the various components of our RAN. Then going down with the network components, we have what is called the open fronthaul interface that connects the DU, so the distributed unit, to the RU, which is the actual radio unit. So this is basically based on some standards which are defined, which are well-defined standards, such as the EEE701 standard. And this is implementing the 3GPP split option 7.2, which is just the number of the split that splits our network in the way that I was showing you. And this is also adopted by Yoren. But at a high level, we have the OpenFront tool that takes care of functionalities between the DU and the RU concerning the control of these components. So for instance, the control plane, also the user plane. So for instance, functionalities regarding the user data. And then we have synchronization functionalities, which compose the S plane. So for instance, to sync the various RUs and DUs. And then we have what is called the M plane, which is the management plane that carries out management operations between the RU and the DUs. We also have many other interfaces. So for instance, we have the O2 between the SMO and the cloud. We have the E1 between that is connecting the control plane and the user plane of the CU. And then we have the F1 interfaces that connect the CU and the DU. And then we have what here is shown like X2, XN, which are other 3GPP interfaces. So that said, this was for the interfaces, but now let's talk a bit about the artificial intelligence and machine learning operations in the Open RAN. So first of all, why do we need this kind of operations and functionalities? So why do we need the artificial intelligence and machine learning operations in the Open RAN? So for example, here there is a picture of the various operations and timescales to which the ORAN architecture complies. We can see that we have some non-real-time loops at the top with the orange shaded boxes that are functionalities that are at timescales larger than 1 second. So for instance, the policy and models or network slices functionalities. Then we have the near real-time RIC, which takes care of functionalities at lower timescales. So between 10 milliseconds and 1 second, and this can be the management of the various user sessions, the load balancing handover on the users, but also some medium access management operations. So for instance, the run slicing operations. So determining how many resources each slice of the network should be allocated, or the scheduling policy that should run on each base station or on each slice of the base station. Then we have what is called real-time loops, which are control loops that go much faster. So with timescales below 10 milliseconds or even below 1 millisecond. And these control loops are not currently standardized by ORAN because the standardization hasn't come to those loops yet. But this concern basically control loops between the RU itself and the DU, or even between the RU-DU and the mobile devices. So for instance, the cellular phones. And this can concern the resource scheduling and beamforming, but also modulation, interference, and blockage detection. So in this ecosystem, why do we need the machine learning and artificial intelligence operation? So for instance, we might want to use these techniques to adapt the network, so adapt the behavior of the network to the actual network conditions that are changing very quickly. So for instance, you deploy a network based on certain conditions, and then as more users join your network or more users leave the network, or even the traffic demand of the users change, the network conditions might change, and you want to adapt the network components to these novel functionalities. So for instance, if at the beginning you have multiple users and then the users leave, you want to maybe reallocate and reduce the resources that are allocated to each base station. We also want to innovate some areas that are typically dominated by heuristics, and to perform what is called model-free optimization. And all of this is done by leveraging some data that is generated by the RAN in real time. Just at a high level here, I'm also showing some, on the left, some application types. So we have on the near real-time RIC, where timescales are large, applications that implement some control functionalities are called R-ups, while at the near real-time rig, we have what is called X-ups. At the real-time rig, however, at the real-time level, however, we have what we propose as D-ups, which are applications that are not standardized by Yoran, but we propose these, and I'm gonna go over them later on. But they run directly on the CUs and DUs. And the D-up, the D stands for distributed applications. And then they can carry out these tasks that require control loops between below 10 milliseconds or even below 1 single millisecond. So what is all that said? What is the life cycle of AI and ML operations in our? So for instance, there's a starting step would be the data collection, because you want to generate a large amount of data and a large amount of data sets that capture the behavior of the network. And that allow you to train some models, some machine learning, artificial intelligence models later on, for which you need a lot of data. So the first operation would be to collect this data from the actual run. Then you have what is called the data preparation. So you take the data that you collected in the previous step, and then you label, process this data, and you prepare this data for the training. So for instance, you might not be interested in all of the data that is collected, but only in some metrics. So for example, only in the throughput, and not maybe in the number of resources that are allocated to each slice. So in this step, you would filter out data and process and prepare for the training. Then the third step is the actual training of the model. And one thing that is worth saying is that all the models that you deploy on the run need to be pre-trained offline. And this is to avoid that untrained models create some outages on the network by taking some random actions. So you can deploy only pre-trained models. And then, of course, you can do some online training to fine-tune the actual model that was already trained, but you want to specialize it to the actual deployment where you're deploying the general and trained model. After this, we have what is called a data validation. So after training, you validate and check that your model performs as you expect it to perform. And then we have what we call a publication and management step, where you take the validated model and you add it to your catalog of models. So the list of all the models that you have that is contained in the SMO and in the non-real-time rig. And this model later on will be deployed on the actual component where it needs to run through the O1 interface that I was mentioning before. For instance, you can have some models that are based on images. So for example, Docker images, where you can deploy the X-up or R-ups or even the D-ups on the Oran nodes. But then you can also deploy some models on nodes that are not typical of Oran. So for example, you can have some models based on some files, for instance, TensorFlow or Keras models. And you can also use these models and this interface to deploy these file-based models on the hosts of interest. After, we have the execution and the inference of the actual model. So the model, after has been added to our catalog, is deployed on our network. And we have the actual execution of the model. And the model retrieves the data from the run through the interfaces that I was mentioning before. So the A1, O1, and E2 interfaces. And for example, the model can be used to perform some inference operations. So the prediction of some future behavior of the network. So the prediction of some KPIs. And then we can have, based on this, also the control of the functionalities and parameters of the network. So for example, you want to reallocate the resources of the network in a smart way. And then we can also have some detection and classification of some traffic that is running on our network. And this is all done through the inference steps of the machine learning model. Finally, we have the seventh step, which is the continuous operation. So once we deployed our general model that was pre-trained offline, we want to perform some online training to fine-tune the model to the actual specific conditions of the network that are happening in that time. So we want our model to adapt to the actual deployment where we are having the model running. And we can also leverage this phase to detect some inefficiencies in our model, or to perform some analytics on the data and provide some feedbacks to the some performance feedback through the interfaces that I was mentioning before. We can deploy single models, or so we can deploy every model that acts on its own. But we can also deploy some models that are chained together to perform some more complex operations that would possible through the single model itself. So for example, this could be the prediction, classification of or control of network functionalities or of traffic. And how do we execute an actual chain of machine learning and artificial intelligence models? So here in the drawing on the right, we see that we have first of all a common data repository, which is storing the data generated by all of our components, and we have this common data repository which is in the near real-time RIC. And this stores all of our data that is generated by our network components. And then we have that connected to this common data repository, we have a data access platform that takes the data from this common data repository and sends the data to our applications. So for example, to the X apps or to our other components. And based on what each XApp needs, so based on what kind of data each XApp needs. So for example, the XApp Y that controls the network slicing functionality would be some data on the actual slices of the network. So the data access platform would send some data regarding these slicing functionalities to the XApp, and then the XApp based on this will perform some control on the slicing profile and send back these as a data to be stored in our common data repository. Or again, the XApp Z, which is controlling scheduling, needs to know some data about the relevant to the scheduling operations of the network, and the data access platform will send this data to the actual XApp. So the task and the objective of this data access platform is to regulate and time the access to the data from our different applications that are running on the data. So it's sort of a middleware between our applications and the repository of data that we have in our network. Another actual very relevant component to this is what is called an orchestrator, and the operations that are the orchestration of the intelligence in the ORAN or in the Open RAN also. So after we have our models and we want to deploy our models, how do we coordinate hundreds of models at the same time? So how do we coordinate the deployment and the running of hundreds of artificial intelligence and machine learning models at once and in an automated way? And how, even more importantly, how do we select the best model that satisfies the operator intent? So about this, imagine a network operator that has an intent that is expressed as the general behavior of I want to change the scheduling decisions of my base stations or of my network in real time to broadcast some video in 4K resolution in a Times Square, so in a certain location. So based on this, we have that we need, first of all, to understand what this intent that the network operator expressed in a high-level language means. So we have to interpret this intent. And then after we interpret this intent, we have to understand which model is best suited to satisfy this intent. After we do this, we need to understand in which point of the network and when to deploy the network intelligence. So where and when to deploy our machine learning model that will carry out the goal of the network operator that was expressed at a high level through a simple human-like language. And after this, after we understand what the intent is, which model we should deploy, where and when, we still need to figure out how to deploy the model. So how to execute the model and how to manage the intelligence. So how to manage the interactions between our run and our model that is running to improve the performance of our network. So in doing this, we have a number of challenges. So one challenge could be the timing. So for example, we need, first of all, to collect our data from our run. And then we have to execute the model, so execute the AI. And then we have to send the output back. But this can be run, for instance, through XApps. So the model can be run through XApps in the near real-time rig. But the time to collect the data, execute the AI, and send the output back requires a lot of time. And we need to be sure that this model conforms to the actual timing scales of the component where the model is deployed. So for instance, for a model deployed in the near real-time rig, we need that all of these operations, so they getting the data from the run, executing some AI, and sending the output back, needs to be within the 10 millisecond time scale that is typical of control loops involving the near real-time rig. Another challenge is the location. So for instance, where do we want to run our model? So if we have an XApp, for example, and our model can run through an XApp, we might want to run our model in the near real-time rig. But for example, is a model deployed in the near real-time rig able to access the data? So, well, this depends on the actual data that the model wants to access and the time required to do this. So, connected to the previous challenge. In this, deploying the AI directly on the edge might help. So we might deploy our models through the apps, which let's remember are distributed applications that run directly on the edge. So on our network nodes, so DUs and CUs, for example, which are being deployed on the network elements, are closer to the data that are generated on the very same network elements. But then we might have other models instead that can afford larger time scales, and they can be deployed as RApps on the non-real-time rig, for instance, and leverage a more centralized view on our network. So another challenge is the location of our actual model. Then we have how to distribute our intelligence. So again, going back to the orchestration, orchestrated intelligence is one of the crucial points in all of this. So how many models do we want to deploy? So how many replicas for each model to achieve the goal of the network operator? And do we need to chain our model? And if yes, how do we chain our models? And are our resources enough to actually execute all the models that we want to execute on our nodes? So all of these are very relevant questions, and orchestration helps us to figure out the answers to these questions. So for instance, we might want to deploy our models all together on the non-real-time rig, but also maybe in certain cases, we want to distribute our models. So in the picture and in the center, we have some models deployed as RApps on the non-real-time rig, but some other models instead are deployed as XApps on the near real-time rig. And again, we might want to distribute even further our models and deploy some functionalities that require faster access to the data and to implement tighter control loops. We might want to deploy them as DApps on the network elements. And in this case, we might want to replicate the same model to the different or multiple network elements. So for example, here, I'm showing the replication of the single DApp they want to deploy on multiple DUs of the network. So the distribution of the of the actual intelligence is another task we have to pay attention to. And then after all, we have the online learning to adapt our model to the actual deployment where we are deploying the model. So let's remember that our model has been trained offline, but then we want to refine our model to the actual network where we are deploying the model. The online learning is a very crucial step and might bring to failures very, very quickly. So for example, if the model says that base station needs to transmit with a certain power, but the base station cannot support that power of transmission, then we have a failure in the model. Or for example, the model says that the base station needs to schedule a user, but then the user cannot be scheduled. That is another failure and can bring to actual disruption in the network, poor performance, or even money loss for the network operation. So the online learning step is another of the crucial steps that we have in this domain, where the general model that was trained on a generic network needs to be refined to what we actually have in the deployment when the model is deployed on the network. And then, of course, getting the data from the run, we might get our models overwhelmed with too much data. And this is because our run generates a lot of data and very quickly. And the question is, do we need all this data that is generated by the run? Well, the answer is probably not. So maybe we can filter out our data to transfer fewer data and only the data that we need. Because in certain cases, maybe some data is correlated, and so having all of that might be redundant. So another consequence of having too much data can be a higher transfer cost, so higher bandwidth between our network elements that are continuously streaming data. And this also can incur in higher latency and congestion in our network. So also the availability of data is good, but the availability of too much data might be detrimental for the network, and we need to select which data we want and how often we want this data. And then, of course, we have challenges related to the security, because all of these data that we have might be prone to attacks. So, for example, you might have some adversaries that are generating fake data, so that the data that you then use to train your machine learning and artificial intelligence models does not correspond to the actual data that is generated in your network, but is containing some fake data that will bring your model to not perform as is intended. And this can bring to some inefficient control, poor performance, can bring to a lack of fairness between your network elements and increase cost. All of this because, for instance, you had what is called a data poisoning, where your legitimate data was augmented with some fake data from some adversaries that want to disrupt your models to bring to inefficiencies in your network. So in all of this, security, and we will go later on security, is a very crucial step in the Open Run. So now that we saw some challenges, let's also see maybe some relevant use cases in all of this. So one of the use cases that I also mentioned in the previous slides is related to the network slices. So network slicing concerns dividing our spectrum in different subportion, and we can manage each subportion of our spectrum that is used by our base station in a different way. So, for example, in the picture on the right, you see that I divided my spectrum in different portions. So I have different colors: green, red, and blue colors, and this corresponds to different applications. So, for instance, the blue spectrum corresponds to massive machine type communication. So, communication, for instance, between different machine or IoT devices. We have the red color represents eMBB, so enhanced mobile broadband traffic. So for example, imagine some video traffic applications that require a lot of data. And then we have the green color, which is the ultra reliable and low latency application. So for instance, if you have some applications that need to send data, the data that they generate very fast to some specific devices. So for instance, for security or alarms in automation in plants and in the industry applications. So all of this brings us to different traffic that each of these applications would generate, and different classes of users, because certain users need a larger data, like video data. Some other users don't need large data, but they require low latency. So for instance, the low latency application. All of these so brings us to different traffic, different user classes, and different requirements. So what we want to do is we want to assign the right amount of resources to each of these slices of the network to support the different applications. Sorry. And we also want to adapt our network as the network goes on, and to adapt the resources of these slices according also to the service level agreements that the operator has with the specific users and to the load of the network. And also we want to isolate the various slices. So we want to have an isolation between the portion of the spectrum that are serving each one of these applications. Then another use cases can be to adopt the scheduling policies inside our network. So going back to the previous example, we still have our spectrum divided in the three applications. So we have the green, the red, and the blue application. And based on the requirements of each one of these applications, we might want to use different scheduling algorithms to these different applications. So for instance, to give some priority to some services, or to give some fairness to other services. And here I'm just mentioning three popular applications. So for instance, the control of the network would have the base station using, for the blue service, a water filling scheduling algorithm. We have the red service that is using a scheduling algorithm that is the proportional fairness. And then we have another algorithm, which is the round robin for the green application. And this is just an example of different algorithms that can be used for the different applications and different slices. And in all of these, we also need to ensure that each of these applications with this kind of control satisfies the service level agreements between the operator and the actual end users. And then we have another use case, which is the orchestration. So if you remember from the previous slides, how do we coordinate hundreds of models at once? And how do we select the best models that satisfy the intents of every operator in our net? So for example, we have an intent and we need to interpret the intent. We need to understand which model satisfies the intent. We need to find out where and when to deploy the network intelligence, and how to deploy this intelligence and execute it in a smart way. So all of this is not trivial, and is actually a very relevant problem studied right now. Sorry. Another case is that of spectrum sharing. So our spectrum might need to be shared between different technologies. So for example, between cellular technologies, so 5G technologies and Wi-Fi, or even 5G and the CBRS band, which is a band that is being released for some very specific use cases and application. And to do this sharing of our spectrum, we might want to leverage some artificial intelligence models to detect the ongoing applications in the spectrum, and maybe prioritize some services with respect to others. And we might want to access our spectrum opportunistically. So for instance, if nobody else is using our spectrum, we might want to utilize the spectrum. But then if there's some technology with higher priority of usage on that spectrum, we want our AI model to figure out that we cannot use the spectrum at that specific time. And then all of these, we have some requirements. So we want to detect the various incumbents, so the primary users that have higher priority on a certain portion of the spectrum. And if these users are present, we might want to vacate our channel fast enough or jump to another frequency to minimize the disruption of the service that we're providing to our cellular users. So for instance, if you have 5G over unlicensed spectrum, so over Wi-Fi, and then a Wi-Fi transmitter wants to start transmitting, you might want to move your Wi-Fi application to another free frequency to not to cause harmful interference to the Wi-Fi application, but also to give a service continuity to your cellular users. Then we have the development of machine learning models and the testing of these models. And this is what we did in our project, which is Coloran, where I will talk about this later. But at a high level, we need some algorithms to generalize over different scenarios and conditions. So once we develop a model and an algorithm, we want this algorithm to generalize to different traffic conditions or different environments. And you want the model to self-adapt to these kind of environments. So, for example, you see that here the picture of an XApp, which will be deployed on the neural time rig. And these has different components. One on the right, where our DRL agent, so our machine learning model, runs, and this component takes care of generating some compressed representation of the data, because maybe we don't want all the raw data that we get from the run, but we need some filtering of this data. Now we have the model that uses this data to control some action of the network. So for instance, the scheduling or slicing policy. And now we have on the left some portion that interfaces our DRL agent with our rig. And this is forming our overall XApp that allows us to receive data from the network and perform some control action. So for instance, some results of our study was that the joint control of our scheduling and slicing resources outperforms the static behavior. So if we have some XApp that can adapt the performance of the network, this is actually beneficial to our network. But then we also have that the way in which we design our model is very important. So for example, we have the best performance where we consider a proper action space that can be taken by our network. And we use some autoencoders to actually reduce the dimensionality of the data. So we just give a simple summary of our data to our model, and we don't give all the data that is coming to our model, because remember, we don't want to overwhelm our model with too much data. On the orchestration that I was mentioning, so the intent-based AI orchestration in Oran, we developed an approach which is called Orchestran. And Orchestran gets the request submitted by the network operator at a high level. So remember, I want to deploy a model in Times Square to give 4K video to my users, and then collects all the requests from our various operators that we can have on the network. And then based on this, computes some orchestration policies, so decides which model to deploy, where and when. So where in the network, on my CU or on my DUs, for example. And then it deploys my actual model on my network. So for example, my model can be deployed as an XApp or an RApp, but also as a DApp directly on the elements of my network. And this also, besides deciding the models to deploy, manages also the life cycle of the deployed models. So once you deploy the model, this orchestrator manages the whole life of our model. So for instance, we will compute some orchestration policy where some models will be deployed on some elements. And then it will deploy the model by filling out some pre-made template of an XApp. So we have generic template applications where we can refine these templates with some machine learning model to deploy it on the network elements. And this model, in this specific case, will be dispatched as a container. So for example, a Docker container that would be implemented an XApp on the neural time rig. And this XApp will then run to achieve the goal of my network operator. And we'll do this by gathering some data from the run, executing some control, executing some intelligence, so some AI or machine learning, and then performing some control on the functionalities of the run. And all of these, let's remember, needs to comply to very strict timescales, which for the neural time rig are below 10 milliseconds from the time where the data comes and to the time where the control is sent back to the actual nodes of the network. And Our results shown that, for instance, we deployed a model which is only controlling the scheduling of our network, and then another model that is controlling jointly the scheduling and the slicing of our network. And we see that deploying additional models in an adaptive way in time can help us to maintain our resources of the network under control in a way that they are not distributed unevenly in the network, and we have a better performance and a faster reaction of the network to potential changes. And for example, adding the slicing functionalities, so deploying the scheduling and slicing functionalities will boost my network performance with respect to only to the beginning of the network, where only the scheduling control XHub was deployed. And all of this was also patched nicely in a framework that is called Open Regime. And this framework that we released publicly to the research community can be used to carry out experimental research in the Open Run. So this is what we call Open Regime, which is an open source toolbox for the development of XApps and in the Open Run and experimentation with these XApps on the Open Run based on the models that are generated. So for instance, Open Regime allows us to perform a collection of data from the actual run. So step one in the drawing on the right. And then we have it allows us to use this data to perform a phase that is called the model design. So where we design the actual AI and ML model. And then we use the data to train and test our model. And finally, when we have a model that has been trained and tested offline, we can deploy it on the near real-time rig as an XApp to perform actual control and interface with our run, so with our CUs and DUs, receive data from these elements and perform some control actions. And of course, this can also be refined through some additional steps of online learning, as I was mentioning in the previous slides. And overall, this model can be used to perform runtime inference and control of our softwareized run. So anybody in the research community can take advantage of this open source framework that allows for a swift and easy design of machine learning models, and then they are testing on a ready-to-use run architecture. But going a little bit more in details, the components that form the Open Regime framework are a near real-time rig, which is running on the Colosseum wireless network emulator, which is a large-scale wireless testbed with software-defined radios, so with real radios that can be controlled for experimentation. And this is, for instance, provided by our Coloran approach that I was mentioning in the previous slides that takes care of the near real-time rig in the network. Then we have some data collection and control capabilities that are carried out by our scope framework that interfaces with cellular protocol stacks, SRS Run and Open Interface, which are open source programs to deploy a cellular network that is running on generic purpose servers and controls real radios. And the scope framework that I will show us in later slides interfaces with these cellular stacks and can perform some control actions, so can change their configuration, but can also send data to the rig through the E2 interface that I was mentioning at the beginning of my presentation. And then we have our experimental platform. So for example, the Colosseum testbed, but also Arena, which is another testbed that we have in Northeastern, or the Power platform, where we can actually use real radios to experiment and build prototypes in the Open Run ecosystem. So the Coloran near real-time rig, which I was also mentioning before, offers an ORAN compliant implementation of a near real-time rig, which is adapted to run specifically on the Colosseum environment, but it can also be brought outside and run on different testbeds, and allows developers to run customized XApps based on a simple template that is provided together with the framework, and allows to, and it already interfaces with the run getting the data and has control capabilities. So the developers can get this skeleton of an XApp. So the pre-made template can augment it with their machine learning model. And then this contains already the functionalities to connect and control to the run, receive data from the run, and send back the control that the machine learning model provided. Then we have the scope framework, which I was mentioning, interfaces with some cellular protocol stacks, and can be run in Colosseum to evaluate solutions, cellular solutions, in different radio frequency scenarios, so in different emulated environments with different kinds of traffic. And for example, Colosseum contains some cellular scenarios that emulate the behavior of cellular environments and deployments in Rome, in Boston, and in Salt Lake City, just to provide some examples. And then we have our XApp development workflow that allows just with these few commands to start a pre-made near real-time rig on Colosseum, to start a cellular network, and to start the XApps that will interface with the run, get data from the run, and perform the control operations to the run. And all of this is done because we want to prototype our solutions in a control environment, which is provided by the Colosseum testbed. But then we also want to validate our models in a testbed with a real wireless environment and not an emulated environment. So for instance, here I'm showing the Arena testbed, that is an indoor testbed that we have in our lab. And then we want to port our solution even further to test the capabilities in city scale platforms, which are platforms with the scale of a small city that are part of the Power program. So we go from a network emulator to a small testbed to a city scale testbed setups. And all of these prototyping our solutions with simple steps that OpenRunGym allows us to do. We actually did that. So we prototype first on Colosseum and then deployed on the other platforms. And for instance, we targeted an application that does the dynamic slicing allocations. And then we saw that even if the quantitative behavior was very different, because these testbeds are very different. One is an emulator and two are large scale platform like Powder and Cosmos, while Arena is an indoor testbed with people going around. We have the qualitative behavior of each one of these use cases was very similar, meaning that prototyping first on Colosseum and then exporting the solution and deploying on testbed with real setups is actually feasible, and allows us to easily design solutions that then work on testbed that are very different and have very different conditions and very different scales and devices. And similarly, we also deployed a rig, implemented some closed loop control through the XApps with our rig. And even in this case, we saw that the qualitative behavior is very similar. And in all of our cases, the XApps that were prototyped on Colosseum and then dispatched outside Colosseum allowed us to reach the final goal that the operation was setting. So for instance, prioritize the users of a certain slice, which is shown in blue in the picture here. So after showing all of these and these frameworks, I would also like to mention some new security challenges that the Open Run introduces, because with open source software, we have very nice functionalities. So for instance, we can interface easily components from different vendors and different manufacturers, but we also need to pay attention to the security aspect of the Open Run, where we have a novel set of challenges to address. So for example, now that we have some open source elements and open interfaces, we have an expanded threat surface with respect to traditional deployments. So for instance, we have a functional split over here, where we have to pay attention to. And then we have some intelligence that is running on the actual rig. So that is also a new possible threat that we need to pay attention to. But then we also have some novel interfaces that are standardized, but they're also open. So they, for instance, we saw the data poisoning effect earlier on. And since we have these all these new interfaces, we also need to pay attention to the threat surface that they expose. While in the case of closed interfaces, we didn't really have this. And on top of this, we have all these elements are virtualized on generic purpose software, where we have to pay attention to the virtualization aspect of this to be sure that this is not leveraged for malicious actions. And as an example, I was mentioning the orange split, which is the 7-2 split. And in this case, we have the RU that can access to the DU through the open frontal interface. And this open frontal interface that allows the communication between the DU and the RU is also prone if we're not careful to some new threats. So we have some challenges where there can be parameter manipulation. So for instance, manipulation of parameter that the DU sends to the RU, or some threats that concern the reconfiguration of the nodes from malicious actors, but also the management of the traffic from the northbound interfaces, the ones that are connected our elements, to perform what is commonly known as a man-in-the-middle attack, where we have somebody in between your interface that is actually behaving in a malicious way. And then we also have some new vulnerabilities that are given by our functional split and interfaces. So for example, new threats can be the unauthorized access to our network elements, so unauthorized access to the DU, the CU, and the RU. And somebody can want to have this unauthorized access to degrade what are the performance of our runs of our network, or even to execute some broader attacks of the network that is actually getting in the way of the availability of our data to our network to run our machine learning and artificial intelligence models, for example. But we can also have what is known as an unprotected synchronization and the control-plane traffic on the open frontal interface. And this would interfere with the integrity of our data and the availability of our data. And more on the availability, we can also have the control plane messages that can be injected to perform some attacks on the user plane. So malicious adversary can modify our control plane messages or send new control plane messages crafted in a specific way, so that some actions are taken on the user plane data, that is the portion managing the actual data that is coming back and forth from the users and the base station. And we can also have an unprotected management of the interfaces where we have some vulnerabilities on the management side and on the management of our network elements. And this, for instance, could cause confidentiality, integrity, and availability problems of our network elements and data. We also mentioned the control loops before. So each one of these control loops needs to be secured in some way. So for example, these are the loops that are currently supported by Yoran. And each of these loops that acts at different levels of time scales needs to be properly secured. So for instance, we have loops between the two RICs that need to be secured, but also loops between the near real-time RIC and our G0B, for example, so our 5G base station, or our with our CU specifically, or between the near real-time RIC and our DU. And then we have what is now left for further studies, so the real-time loops that need to be secured for what concern communication and loops between our DU and RU and mobile devices. So all of this is not trivial and is actually a very sensitive research topic. And then we have also loops that can happen inside a single mobile device, for example. Among the new vulnerabilities that the intelligent component exposes, we can have new threats where we have the near real-time RIC applications, so the XApps, that are potentially crafted by third parties, but also that there can be some potential attackers that craft some applications to perform against some carriers. Or we can have some vulnerabilities that concern disabling the encryption between our components to perform some eavesdropping on the information that is going back and forth between the components. Again, we can have some signaling conflicts between the control of the near real-time rig or the G0B for what concerns the control plane. Or we can have even conflicts between all of our applications that are either sending the same control or exposing an inconsistent behavior. And then we can also have denial of service attacks performed on our applications or through our applications, and some privacy concerns. So, for example, we don't want the rig to be able to identify the specific users, but we want some aggregation of the data from the users that is anonymized data to get to our X apps and our apps. And on these, we can have our X apps that can be misconfigured through our A1 interface to actually track our users. So this could be a vulnerability, so the tracking of our users that instead are supposed to be anonymized information that are available on the X apps. And more on the data injection, we can have some adversaries that inject some data in our X apps to have incorrect behaviors from the X apps to the control and ultimately to the run. And then talking about the cloud, we can have new attacks that concern the virtualized environment. So for instance, we can compromise the virtual functionalities of the network. We can have some exploitation of the E2 interface, so from the rig to our cloud. And we can have some misuse of our containers or of our virtual machines to implement some malicious behavior in the network. Or we can even have other attacks that are concerning the spoofing or the compromising of the underlying network or services that are exposed on the network. And this is just a short list of all the new security challenges that this approach is actually bringing us to. So all of this to say and to conclude that the Open Run allows us to perform some dynamic control loops through, for instance, machine learning and artificial intelligence control. So this is very good, but we also need, this also brings novel challenges that we didn't have before. And with these challenges, we can also have some new vulnerabilities that are very specific to this new Open Run paradigm, and we need to adapt and to control and to learn how to work on. And this was it on my side. I hope you enjoyed this seminar. And if you have any questions,